Vishak Narayanan is a computer system architect enthusiast, currently pursuing his PhD degree in computer engineering at Iowa State University of Science and Technology. His research interests and technical skills mainly focus on modeling, designing, and evaluating batteryless computer system architecture. Going forward, he intends to extend research paths investigating strong linkage between microarchitecture of ultra-low power sensor nodes and energy harvesting front ends. Let's welcome Vishak.
Thank you so much, Dr. Sahu, for the introduction. Good afternoon. I'm Vishak Narayanan. I'm really excited to be presenting my work on developing BOBBER as a prototyping platform for batteryless intermittent accelerators. So, pervasive edge intelligence promises ubiquitous deployment of sensor nodes that could revolutionize society from agriculture to manufacturing to smart infrastructure and to beyond. The idea here is to have these sensor nodes deployed in hard-to-access locations where they can perform intelligent computations, near sense data, and occasionally communicate back to the cloud. Therefore, such nodes must have low cost, be easy to develop, and have limited maintenance over long life with very less user intervention. The traditional way to power such sensor nodes is batteries. However, the pervasive deployment of billions to trillions of sensor nodes poses a challenge for battery-powered devices. Using batteries increases the cost, limits lifetime, requires high maintenance, and are not at all environmentally friendly. Alternatively, the batteryless sensor node paradigm has emerged where a sensor node survives solely on ambient or wirelessly harvested energy. Any energy buffering is done using capacitors or supercapacitors rather than batteries. The result is lower cost, initial and ongoing, longer lifetime, and environmentally friendly sensor nodes. Therefore, batteryless sensor nodes provide significant potential for pervasive computing applications. Unfortunately, the rate of energy harvesting is often very low and variable. For example, consider the trace of an RF energy harvesting from a 3-watt 915 source. The harvested power may be above 0 dBm, which is a milliwatt, but it's often beneath a milliwatt. A commercial ultra-low power microcontroller may need above a milliwatt to actively perform computations and make decisions. As a result, the intermittent execution paradigm has emerged where the system banks the harvested energy into a capacitor until enough energy is collected to turn on and perform sensing, communication, and computational tasks. Once these tasks are completed or the energy has been exhausted, the system dies to allow the capacitor to recharge. This type of intermittent operation, although comes with significant challenges, a few including loss of all state that's not stored in the non-volatile memory, uncontrollable harvesting rates, and short on times. Essentially, there is very tight coupling between the harvesting front end and the timing of when and how a commutation is performed. Given such tight coupling between energy harvesting and computation, the batteryless systems research has relied on real-world prototyping systems and platforms. The most prominent is WISP in 2007, but also includes Flickr and Capybara that's more recent. Alongside these, debugging and evaluation tools have been developed to help in the debugging, to debug in the challenging context of energy harvesting. That's EDB and ECO. Until now, work on design of batteryless computational engines have been performed primarily in simulation or rarely in expensive and time-consuming ASIC fabrication. Until now, there has been no rapid prototyping platform for intermittent accelerators. Therefore, to spur research into hardware acceleration for intermittent sensor nodes, the goal of this work is to develop a platform to quickly prototype and evaluate intermittent accelerators under real energy harvesting conditions. To achieve this goal, we developed BOBBER. BOBBER is a single PCB board which has an RF energy harvester circuit along with an MSP430 microcontroller to run system software, including power control, and an Igloo Nano FPGA to host accelerator prototypes. Importantly, we must consider the volatility of our state components. The MSP430 has a small amount of volatile SRAM for the stack that's backed by an onboard FRAM, which is a byte updatable non-volatile memory. This FRAM can be read or written in 1 to 2 cycles and is used for both instructions and data. Small amounts of volatile data can be quickly checkpointed to the FRAM before the power is lost. On the other hand, the Igloo Nano has a volatile SRAM for data, while its logic bitstream programming is non-volatile, which actually allows it to have short boot times after being unpowered. Of course, this leads to a potential correctness issue, and to show this, consider this following example. This program simply does multiply accumulates to an array A to each element of an array A that resides in the FRAM of the microcontroller. BOBBER uses a compute kernel template to run this multiply accumulates. The compute kernel sits on the application software on top of an intermittency-aware firmware. The kernels are accelerated by the FPGA and the computation is broken down into tiles of size 4 in this example, where each tile is actually computed on the accelerator. First, we reset the FPGA and send the elements of array A from FRAM on the microcontroller to the SRAM on the FPGA. Second, we start the computation. Third, when it's complete, we read the updated elements, all the results, back to the MCU's FRAM. Under normal operation, this would work really well. However, consider a power failure that occurs inside a compute kernel after a compute instruction has been completed, but before the results are actually read back into the microcontroller. Assuming that we checkpoint the volatile program state of the microcontroller into the non-volatile FRAM, MSP430 would boot up after a power failure and continue from where the power failure had occurred. The results read back from the accelerator would be the random startup values that is present in the volatile SRAM of the FPGA. So what we do is continue to use the checkpointing on the MSP430, but force a re-execution of the compute kernel if we sense a power failure had occurred during its execution, resending all lost volatile data for a particular tile and making the kernel compute templates idempotent. For the details are in the paper and in the published software. So now that we have the platform, how can it be used to implement an application for pervasive intelligence and evaluate potential optimizations? To answer these questions, we developed a basic multiply accumulate accelerator for convolutions and modified a TF-Lite micro runtime system to use these for 2D convolution and depthwise operators. We then ran a LaneNet5 model that is trained for Ames dataset on our system. Most importantly, BOBBER works in with real-world intermittent power, guaranteeing correctness in program execution. BOBBER in continuous power achieves 1.9x more performance, and in order to ensure forward progress in intermittent power, we must tile the computation to fit within the available on time. Due to this, BOBBER's performance with tiling drops to 1.3x in continuous power due to increased data movement and redundant computation from tiling, suggesting there are opportunities for optimization. BOBBER also allows exploration of such different computational optimizations. As we have larger tile sizes in intermittent power, there is an increased amount of wasted energy due to lost partial computations for resending volatile data and recomputations. BOBBER inherently allows selection of the right tile size depending on the available on time, and also provides techniques that can save this wasted energy. So going forward, first we would like to optimize BOBBER to make it more energy efficient in intermittent power by removing significant overheads due to the reference design size of the LDO, the FPGA's 20 MHz oscillator, the dynamic power consumption of the FPGA, along with techniques to reduce the SPI overheads that would eventually reduce the MSP430's dynamic power. In parallel, we are also working to increase the number of TinyML applications that BOBBER can support. Finally, BOBBER opens the door for many research on intermittent accelerators or microarchitectures using FPGAs, a few including power adaptive reconfigurable accelerators or microarchitectures reconfigured that's based on the rate of harvested energy, energy model driven scheduling for heterogeneous application workloads accelerated by the FPGA, achieving a more dependable and timely execution for these workloads. At the same time, I would love to talk more about your ideas, so please visit me during my poster session. Thank you for listening.
Any questions? Okay, one over there. Matt, could you pass? Yeah.
So the MSP430 has an analog input on it. Why can't you just look at the capacitor and determine that you have enough power to make it through the computation before you start the long computation? And that way you don't lose any energy in the computation that's not finished.
Yep, that's a good question. And we actually use the ADC that the MSP430 provide to sense the power. But the computational time with respect to the energy store that we have, the energy buffer size that we have, it supersedes the computational time. So in the challenging context of intermittent computing that we have, we will not be able to complete a full compute cycle within whatever energy budget we have. But the way the solution works is basically it detects how much power is available on the front end, and it then checkpoints, or if it detects a power failure, it would re-execute the compute kernel. But the platform mainly solves the problem of correctness issues. When if you cannot complete at least a full operator within the available power budget.